Hello, this is Nicholas Vinan from Silicon Chip Magazine, and I'd like to talk to you today about this power LCR meter design that was published in the magazine, March and April 2025 issues. So LCR, if you're not familiar, stands for inductance, capacitance, resistance. So this can measure all three, but really its aim is measuring inductance, the L part. And the reason for that is that firstly, a lot of multimeters don't measure inductance. You often need a specialized piece of equipment called an LC meter to do that. But most importantly, even if you have an LC meter, it usually only measures the inductance of an inductor at a low current. That's not really ideal because usually, well, in many cases, when you're using an inductor, you're putting quite a bit of current through it. And what can happen is the inductance can vary quite a bit with the current. If you don't know that, then it's difficult to design a circuit that will function properly, especially if you're making your own inductor because you're not going to have any data on it. And it's actually quite easy to make your own inductor because all you really need is some sort of a core, often a toroidal core, and some wire, and you wind the wire around the core and you have an inductor. And in fact, you don't even need a core. You can just get a coil of wire and that's an inductor. Now, the air core coil, the one without a core, actually is not really a concern because technically its inductance doesn't vary with current. And that's the advantage of an air core inductor. But the disadvantage is they're big and heavy and expensive. So often you'll want a core. The core will affect how the inductance varies with current. So how do you know? Well, you use this device. It tells you, it basically plots a curve. And we can see later in the article here, here are some example scope grabs of an inductor with a fixed voltage applying. Now, if you had a perfect inductor, it will be a straight line. You can see these lines are far from straight. And what's happening is that the inductance is reducing as the current builds, and therefore the current builds faster. Well, in this case, it's actually, this is a case where it's actually pretty flat. And here are some other cases. Here you can see some pretty a distinct kink here. So this is an inductor that holds its inductance for until it gets to about an amp, and then it drops off rapidly and the voltage shoots up. So this is the sort of thing this device can tell you. It's something you can build yourself. We have the circuit board. There's a parts list, which if you look in the article here, here's the list of parts you need. So you can put it together yourself, and we have the instructions on how to do that. But this first article that was in the March magazine concentrates on explaining how it works. So we have a little diagram here of a very simplified circuit that shows the inductor here connected across a MOSFET. Now, really the reason that this MOSFET is here is because you can also connect a capacitor. If you look at the specifications, it can measure inductance with currents up to 30 amps, but it can also measure capacitance and resistance. The capacitance measurement doesn't go very low, but it does go pretty high above a farad. So it's pretty good for measuring big capacitors. And the resistance measurement goes very low down to a milliohm. So it's good for measuring power resistors or shunts. These are things you can't often do with your regular multimeter. It's just not accurate enough, or it won't go that high or that low. But as I said, the main function is measuring inductance. So if you put a capacitor there, you wanted to have it discharged before you start the test. So that's why we have a discharge MOSFET. With an inductor, I mean, there is energy stored in an inductor, and it's good to discharge it before the test, but it would discharge itself basically if it did nothing. So the main reason for that MOSFET is if it's a capacitor. Now we have this switch here that switches the current through the device. So initially at the start of the test, there's no current. This MOSFET switches on. You can see from the diagram up here, the current ramps up, and then it switches the MOSFET off. Now there's also a current sink. So there's two different ways you can pull current through the device, either essentially connecting the supply voltage across it and monitoring the current using this shunt here, or applying a fixed current through this sink and then monitoring the voltage. When it's measured, so that the current's monitored by the fact that any current passing through the device, and this switch also passes through the shunt, which develops a voltage across the shunt, which is amplified and fed to the microcontroller. So it can see how the current changes over time. It can also see how the voltage changes over time because there's an amplifier connected across the device that's also feeding the microcontroller. So basically it can plot a VI curve, and from that you can determine inductance and things like that. There's also a DAC here controlled by the microcontroller. That's a digital to analog converter. So it can produce an analog voltage that's used to control how much current sink pulls through the device. So that looks relatively straightforward. Now, if we turn over to the actual circuit, this is only part of the circuit. You can see it's quite a bit more complicated, but a lot of that's just the details of how things are driven. So this is the main test part, and then if we look over here, here's the microcontroller that controls it, and here's the power supply. These are pretty straightforward. The most interesting part is here, and these blue labels here where it says RC1120, that's showing that this point in the circuit goes to that pin on the microcontroller. So obviously the red arrows here are to the power supply. So this circuit here obviously needs power, and it also needs control. So that's what the red and blue arrows are for, and everything else is the actual control circuitry here that does the testing. So this DUT over here, this is the Con 5 and Con 6 of the terminals where we connect our device, such as an inductor. You can see the positive end goes straight to this 10-volt filtered rail, which has quite a lot of capacitors on it to make sure that it holds up when there's a lot of current flowing through the device. These 47 MF is 47 millifarads, or 47,000 microfarads. So there's about a tenth of a farad of capacitance on this rail, which is substantial, and that's required so that the rail doesn't sag too badly during the test. And the current will then flow to this terminal through the device, out of this terminal, and then through this MOSFET when it's switched on, and a 5 milliohm shunt to ground. So that's the loop through which the current flows. The 5 milliohm shunt produces 5 millivolts for every amp through it. That's then amplified by IC8, and that goes to the microcontroller so it can measure the current. It also goes to this comparator here. The other side of the comparator connects to the DAC, the first output A. So in other words, by setting a voltage at this output A in the DAC, we set a trip threshold. When the current exceeds it, it sets the reset pin of IC3B, which switches off the drive to the gate of MOSFET Q4. So that's a safety feature, or it's also part of the testing feature, that we can program a current at which it will switch off. And then the other part of the DAC controls this Darlington transistor here, which is that current sink. So when the MOSFET is off, it can switch on the transistor to, say, pull 100 milliamps through the device. So in the case where that's a capacitor, it might do that to charge it at a certain rate and then measure how long it takes to reach a certain voltage. And from that, it can calculate the capacitance. And similarly for a resistor, if you program a current through a resistor, measure the voltage, you can calculate the resistance. There are actually two ways that it measures the voltage. So the first way is that here's another current sense amplifier, identical to the one used for this shunt, but it's used instead to connect across the device, and that's for measuring small voltages because it has a gain of, I think, about 50 times, and that then goes to the microcontroller. So when there's a small voltage across the device, it can measure it here. If there's a large voltage, we have instead this differential amplifier here, which has a much lower gain, but it also feeds the microcontroller through a different pin. So it's effectively auto-ranging. It has two different voltage ranges it can monitor. Here's the discharge MOSFET connected across the device with some level shifting circuitry, so you can switch that on when necessary to discharge the device. And then this flip-flop here, well, we've already talked about how when the current gets too high, it switches off the MOSFET, but obviously there's also the need to switch it on, so the microcontroller controls that through these pins here. So the microcontroller sets everything up, switches the MOSFET on, the MOSFET will pull current through the device, the microcontroller can make measurements, the microcontroller can then switch the MOSFET off, or if the current limit is reached, it will automatically switch off. So that's basically how the testing works, and you can see here from these scope grabs in these tables how it's actually the yellow trace is the MOSFET gate, switches on. You can see how the current through the inductor rises, and then eventually it switches off. And throughout this rise, it will be making samples of the voltage and current, and then that's used to calculate the results. And I think if we look at part 2 here, firstly, part 2 shows how to actually assemble the circuit board. So here's the board and all the parts that you put on it. Almost everything is on one side of the board. The other side just has some switches and the terminals that pass through holes. And you can see how it fits in the case and the panel drilling. But what we're interested in is it's not actually here. Let's go back to part 1 to see if it shows us some results. This shows the results from the actual device for several different inductors that were tested. And what it does is it will measure the inductance at 10 different currents, and you can step through and you can see the current and the inductance and therefore how it varies. So in this case, you can see that at 2.2 amps is 44 microhenry. So Interestingly, this inductor is rated only at 21 microhenries, so it's actually quite a bit higher inductance at low currents, which is something you wouldn't necessarily realize unless you tested it with a device like this. And then as the current steps up, you can see it drops slowly, reaches its rated inductance at about 10 amps, which is exactly what the rating is. So in other words, this inductor clearly meets its specifications. But then we can see that as we exceed 10 amps, it still has significant inductance at 12.4 amps. It's down by about a quarter at 15 amps, down to about a half at 20 amps, and then it continues to fall off 24.4. So that's a pretty graceful fall off in inductance with current. You'll see that there are other, well, here's an air cored inductor, and as I said earlier, they don't vary with current, so that's proof of that between 1 amp and 8 amp, it's exactly 1.8 millihenries. Here's another air cored inductor. Again, it doesn't vary very much. But then you have inductors like this one here. So it's a transformer, which is also an inductor, but it's not designed to be used as an inductor. But you can see that at 1 amp at 16 microhenries, by 3 amps it's down to 4. It's a quarter of its original inductance. So it has a very sharp fall off as the current rises. So that's what this device will tell you, and it's actually very useful, especially if you're trying to make your own inductor for a switch mode power supply or something like that. You need, say it's a 3 amp switch mode power supply, you know that you need about 5 amps peak current. Well, you better make sure your inductor still has sufficient inductance at 5 amps to do its job. There are actually stability concerns. If you can do the mathematics, you realize that when you're designing switch mode supply, you need a certain amount of inductance for stability, and you might have an inductor that's, say, rated at 100 microhenries, but maybe drops off to 50 microhenries by 5 amps. That might not, your supply may no longer be stable, so you need to check that, and that's what this device is for. So part 1 of the article has the circuit description, the circuit diagrams, the parts list, and then if you look at part 2, then we have the circuit board assembly instructions, this overlay diagram that shows you what goes where, how to solder the cable to the screen, how to assemble it into the box, cutting the holes for the LCD and the buttons and switches. And then we have some information on calibration here, and then some hints on using it. So it's a fairly complicated device, but once you've built it, it basically just works. So in fact, you can see here, interestingly, he's designed it to take these 2 large capacitors. In many cases, you only need one. It doesn't hurt to have both, other than the fact that you have to buy 2. But for many applications, 1 is good enough. So he's tested that and verified that as well. So that's the Power LCR meter. It's a pretty nice bit of test equipment, especially if you're making your own inductors or sourcing inductors where you don't have a lot of data on them. You don't know how their inductance is going to vary with current. And not a cheap device to build, but not going to break the bank either. But it's a pretty specialized and useful piece of test equipment. I hope you found that interesting. Check it out in Silicon Chip Magazine, March and April 2025 issues. Thank you for listening.